In previous videos, we have dealt with the origin of the universe and our planet. We also talked about atoms, elements, and minerals to understand the rock cycle. At a much larger scale, we reviewed the continental rift hypothesis and plate tectonics. However, how do we know that all that has occurred in the history of our planet? And more importantly, when all these things happened? The when is what this video is about. This video deals with the way we measure time in geology and how we determine the age of rocks, and therefore the events recorded on them. Enjoy it and don't forget to like, share, and subscribe. We know that the Earth is old, but how old really? More importantly, how do we know it? One of the major subdivisions of geology is historical geology, where we arrange the events that have occurred and shape our planet in the present form we see it. Perhaps one of the most difficult things to grasp by any person is to really contemplate the astounding duration of geologic time. This is key to understanding the uniformitarian principle due to the slow rates at which geological processes take place and the quantities of time involved. Although geological time goes on slowly, including the internal and external processes, the incredible amount of time has led to the formation of our modern landscapes, including geological wonders. Indeed, extraordinary geological features. When we study the history of our planet and the events that have taken place, a really important question is, how do we measure geologic time? We have different ways of measuring geologic time. Some methods are more intuitive and straightforward, others require different analytical techniques. To assess the age of a particular rock, stratum, or event, we can use the following methods. Relative dating. This is whether one rock is older than another based on their spatial relationships. We can also employ fossils because we have a detailed record of the evolution of life on Earth. We can also employ absolute dating methods by using isotopic techniques to determine the actual ages of the rocks. These three methods are useful, and which one to use will largely depend on what is the objective or interest of a particular study, since each one provides a different level of accuracy and uses different principles. Let's talk about them in more detail. Early time scales simply place the events of the Earth's history in a proper sequence or order, without knowledge of how long ago in years they occurred or how long a particular event lasted. For example, dinosaurs' skeletons were identified a long time ago, but the duration of how long they reigned on Earth was not fully established until recently. When we refer to something as being relative, it means that something is considered in relation or in proportion to something else, or something having or standing in some relationship or connection to something else. Well, in this case, for example, if we analyze strata, we say that this layer here was before, so that this layer now can sit atop. So this layer was here before, therefore is older than this one that came to rest atop, therefore is younger. This first fundamental principle is known as the law of superposition and was formulated by the Danish polymath Nicolas Steno. In addition, Steno formulated three more principles fundamental to the field of sedimentary geology. These are the principle of original horizontality, the principle of lateral continuity, and the principle of cross-cutting relationships. These four principles in total provide the foundation basis of the discipline of stratigraphy.
Hey guys, this is a great place to talk about a fundamental principle in geology, perhaps one of the most important in sedimentary geology and stratigraphy. That is the Steno's law. It is named after Nicolas Steno, who formulated this fundamental principle that states that in a conformable succession of sediments, the layers that were deposited at the base took place first than the position of the successive layer on top, and so on. Therefore, the layer at the base is older than the layer that is resting atop, and successively, the third layer, like in this outcrop, is much younger than the latter two layers. And it allowed us to somehow reconstruct the history of this particular succession. It gave us a sort of relative dating way where we can understand what happened first and what came in second. And it is important to understand this principle because that's one of the fundamental bases for stratigraphy. As a strata pile up on top of each other, we can reconstruct like a booklet the history of the Earth.
However, there is also another way to date rocks and strata by using another relative age dating technique, that is, using the principle of cross-cutting relationships. This is that a stratigraphic relationship follows the fact that for a stratum to be modified, intruded, or superseded, it has to be there before in a way that the new event, whatever it is, modify the original layout of the previously existing or older event. Let's illustrate this with the following example.
Now, check out this rock cropping out the sea. Here, we see these almost vertical beds cutting up along this rock. This is an igneous intrusion called a dike. It cuts into previously existing, therefore older rocks. We call this an intrusion where the host rock gets intruded by the new or younger rock as hot fluids ascend into the host rock.
This way, we can organize the sequence of events that resulted in this arrangement of lithologies, bed boundaries, and intrusions. This way, we can understand the order in which things happened, and we can begin reconstructing the events that took place in a particular location. Since the discovery of William Smith that the fossil content of a particular stratum can provide an orderly arrangement of geologic time, it has served as the basis to establish the geologic time scale. It also provides a detailed record of the evolution of life on Earth, and that is important because we can see evolutionary patterns, appearance and disappearance of a species, and we can see how animals and plants change through catastrophic events, for example, climatic changes or the variability in the distribution of land masses and circulation patterns, for example, those caused by continental drift.
Check out this diagram here. This rock can be correlatable to this one because these fossils are found in them, even though they are located far away from each other. Now, check out this rock. Look at all these fossils. These are species that are unique to this particular strata. They have a range of appearance and disappearance in the rock record. Thus, any stratum anywhere else in another location are likely to share the same age. Thus, we say that they can be correlatable or that they are age equivalent to each other. This way, we can correlate both based on the fossil content, beds that are in different locations, even over vast distances across the planet.
His original proponent, William Smith, called this the principle of faunal succession, and it is based on the fact that the fossil content in a sedimentary succession occurs in a specific order. This order is reliable and predictable where fossils can be used to correlate age-equivalent sediments over vast distances. Thus, it is of great importance in determining the relative age of rocks and strata. This method follows up on the principles of stratigraphy, but deals with the fossil content of a particular rock. It is the fundamental concept of a discipline called biostratigraphy, which in turn is one of the most important techniques in the field of sedimentary geology. Advances on the understanding of the atomic structure and properties such as radioactivity allowed us to accurately determine numerical dates for rocks. To do that, we use radioactivity, a spontaneous property of some particular elements contained in rocks. To do that, we need to understand that some elements decay naturally with time, but how much or how fast? Well, to understand that we need to understand this concept, the half-life time. That is the time required for a quantity of substance to reduce to half of its initial value. This happens because some materials contain an unstable nucleus, so they disintegrate as the unstable atomic nucleus loses energy by radiation. Three of the most common types of decay are alpha, beta, and gamma decay. The original term half-life period dates back to 1907 when this gentleman, Ernest Rutherford, discovered this principle. This provides a quantitative assessment of a particular rock strata that was formed during a particular period of time. It allows further refinement of the already existing relative age dating and the biostratigraphy age dating provided by the fossil content of a particular stratum. Several radioactive elements allow for different antiquity depending on the half-life time of them. To date relatively recent events, we use carbon-14, the radioactive isotope of carbon. Because of the half-life of carbon-14 is only 5,730 years, it can be used for dating events from the historic past as well as those from the very recent geologic history, as in some cases it can be employed to date event as far back as 70,000 years. Thus, radiocarbon dating is widely employed in other disciplines such as archaeology. For older rocks, these are the most frequently employed isotopes in radiometric dating.
Note that each one of these methods is limited by the half-life values. For instance, potassium-40 is a radioactive isotope of potassium that decays into argon-40. The half-life of potassium-40 is 1.3 billion years, far longer than that of carbon-14, allowing much older samples to be dated.
but not quite enough to date rocks that go further back into the beginning of the Proterozoic, for example. For those, we will need one of these other isotopes. This is the geologic time scale, an amazing orderly arrangement of the entire 4.6 billion years of history of our planet into different hierarchical units of geologic time, such as eons, eras, periods, and epochs. They are separated by specific numerical ages with a certain degree of error, so that we can allocate not only a specific time when something occurred, but also how long it lasted. So this way we know what happened first, when and how long it lasted, and also what happened next. That's quite amazing. What is amazing is that here, every color has a different meaning, and everything that has happened in the history of the planet occurred somewhere here. From the formation of the Earth itself, to the formation of the atmosphere and the oceans, the origin of life, every mass extinction, all the glaciations, and the origin of humanity to today, everything occurred somewhere here. At some point, the basic unit of measurement here, the 1 million years, give us the age in million years before the present of each one of those events. Quite amazing, hey? Let's take this chronological unit for example, the Permian. We can say the Permian is the last period of the Paleozoic era. It spans 47 million years from the end of the Carboniferous period, 298.9 million years ago, to the beginning of the Triassic period, 251,902 million years ago, and is subdivided into 3 epochs: Silurian, Guadalupian, and Lopingian. Thus, this orderly arrangement of events, its durations, and resulting features is part of historical geology, a fascinating branch of geology that continues to evolve with every discovery and the evolution of the concepts and analytical techniques. Arguably, the establishment of the geologic time scale and the discovery that the Earth has a very long and complex history is perhaps one of the most impressive contributions of geology to humanity. Understanding that the Earth is old allowed us to understanding how a landscape changes over long spans of time, and also provides time for gradual change in evolution of plants and animals. It also allows us to understand how continents move, come together, and break apart again. More importantly, it helps us as a species to understand our own changes through time and the adaptations we have undergone to survive as a species. For example, how humans underwent last glacial maximum. More importantly, establishing geologic time allowed us to organize and understand the past to draw knowledge to predict our very own future. Well, thank you for watching up to this point. I hope this video contributes to increase your admiration and amazement towards our planet and the way we understand it. Please let me know in the comment box which one you think is your favorite technique to date how old is the Earth, and more importantly, why. About me, well, I quite like fossils, as you know, so it's got to be using the fossil assemblage of a particular stratum. And why? Because when we combine fossils and strata, it can give us also a detailed record of the evolution of life on Earth. I think life is a miracle, and I find this evolution through time even more fascinating. And you? Please let me know in the comment box, and I will do my best to answer all of them. Don't forget to like, share, and subscribe, and I will see you in our next video. Ciao!